Welcome, everyone, to our webinar on 5 new things every new ClickHouse user should know. We're going to be particularly focused on things you'd like to know if you're building applications. My name is Robert Hodges. I am CEO of Altinity. And another title for this talk that I thought about is 5 things I really like about ClickHouse and want to share today. So I hope you'll appreciate the enthusiasm about these different features we'll be talking about. Let's just jump in and do a little bit of housekeeping. So this talk is being recorded. You don't have to scramble to take notes. We will distribute a link to the recording as well as the slides within about 24 hours, probably less. So you'll get it in your mailbox and you can look at it yourself. Then a couple other things. So we do have time for questions. You can put them into the Q&A box, or you can put them into the chat. We don't really care. If things are relevant to the talk and they pop up, I'll probably just stop and answer them right there. Otherwise, we'll have a bit of time at the end. And my colleague, Josh Lee, who is helping me today, he's our dev advocate, will also be watching for questions and queuing them up. So with that, let's dive in and we'll have a quick message from our sponsor. We're Altinity, and we help you run open source ClickHouse better. We've been around since 2017. We have hundreds of customers. Our 2 main offerings are Altinity.cloud. So we'll talk a little bit about it in one of the slides, but it allows you to run ClickHouse in open source ClickHouse, any build, practically anywhere you want. We also have enterprise support. So if you want to run ClickHouse on Android phones, give us a call. You want to run it in clusters in Azure with hundreds of servers, give us a call. We handle all of that. Just one more thing, we are not ClickHouse Incorporated. It's very important to stress that. We are a different company. We actually compete with ClickHouse Incorporated at a business level, but of course we collaborate on code. We've, among other things, put in hundreds of commits or submitted, had something like 600 plus merged PRs in ClickHouse. We are also the authors of things like the Altinity Kubernetes operator for ClickHouse, the Altinity backup, also known as ClickHouse backup, and a number of other features that you may already be using. And we do ClickHouse builds. So with that, let's jump in. And for those of you who are new and have been living under a rock, the first question is, what is a ClickHouse? Let's just have a quick intro. So if you're not familiar with ClickHouse and this is your first time hearing about it, it's a real-time analytic database. You can think of it as combining the best features of an open source database like MySQL, a relational database, and analytic databases. So from the MySQL side, you get things like, hey, we understand SQL. It runs anywhere. It's open source. From the analytic database side, we get things like storing data in columns, being able to use parallel and vectorized executions so that we can get very, very fast results, being able to scale to many petabytes. ClickHouse is open source, of course. It's Apache 2.0 license, and that's a great license. Places virtually no restrictions on what you can do with it, and so you can build your own products on it, so on and so forth. And because of these properties, ClickHouse has become extremely popular. So it has about 41,000 plus stars on GitHub. That's about the same number of stars as Spark, and it's used for all kinds of use cases, from observability to real-time marketing. Okay, let's just jump into the meat of the talk. So lesson number one, or thing number one to think about, ClickHouse runs anywhere. I mentioned running on Android phones. That's actually not a joke. It was Alexander Kuzmenkov wrote a blog article back in 2020 where he did exactly that. And probably not something you want to do for production systems, but it really does run anywhere. So what you want to do is find the way of running it that works for you. One of the ways that I often run ClickHouse is using this very, very simple installation, which works off the clickhouse.com site. It's probably the simplest install you've ever seen. There are other products that do this as well. It's a well-known trick where you just say curl, give the name of the website, pass it to bash. And what it does is it will grab the ClickHouse binary, drop it onto your into your into the directory where you run it, and set it to executable. At that point, you can just start it. It is super easy if you just want to play around with ClickHouse and you want to look at it. It is a little bit difficult for beginners to use because if you want to do any kind of configuration, you really have to know your way around the ClickHouse directory that gets set up and understand how configuration files work. But if you know those things, it's super convenient. It allows you to have ClickHouse right there on the command line. You can watch the logs. It's very convenient. Now, if you're on Linux and you want something a little bit more conventional, and in fact, in a lot of enterprise environments, this is how you would do it. You would install using apt or RPM. Both both types of packaging are supported by ClickHouse, along with just regular binaries. Um, and as you're doing this, you have a couple choices of builds. You can use what are called official builds, which are directly from ClickHouse Incorporated. They appear every month. They have two what are called long-term support releases per year, and those LTS releases have a year of support. So you can go find out how to install those over at the URL that's shown below. We at Altinity do what we call Altinity stable builds, and they are designed for people who want stability. We give a 3-year tail on support. We don't release them until we're pretty sure they're stable. In fact, really sure. We do collect a lot of customer information. And then what we'll do over those 3 years is, in addition to fixing bugs, we'll even backport features so that you don't have to upgrade. So these are a great option if you're the kind of person who likes to upgrade major versions, say, every 2 years or so. Now, there's a fourth way that you can get ClickHouse, which is to use containers. And these are very, very popular because they're so simple and allow you to basically drop the container, onto your desktop and run it with Docker. So here's an example of using a Docker run to pull up an Altinity stable build, give it a name. There's a few options that we set here. For example, host networking so that it just automatically maps the ports. But if you do this, it'll just come up bang and off you go. This is kind of nice for platforms like Mac OS, where there are Mac OS builds for ClickHouse, but it's usually more convenient to just run it in Docker. You can also run it in Docker Compose. That's very, very common. It works great. And in fact, ClickHouse uses Docker Compose heavily for testing. So it's something that's very, very well tested. And if you want to try building a complete system, it's a great way to do it. There's Kubernetes, of course, speaking of containers. So if you want to run at scale, uh, you can set it up on Kubernetes. I mentioned the Altinity operator already. That you can simply Google it. You'll find it very quickly. That allows you to, with a very simple resource definition, you can, you can create a simple file. We have many videos and examples of this. 12 inches of YAML, and bang, you've got a full cluster. The big advantage of Kubernetes for building systems is it allows you to iterate through a lot of different combinations of CPU, storage, replicas, shards, things like that. You can do these and set these up basically in a few minutes. So they are it's super efficient. And then the final thing is, if you're just all about convenience, you can run this stuff in a cloud. Two major clouds. There's ClickHouse Cloud. That's a SaaS version of ClickHouse. It has a Snowflake-like convenience and built-in tools. There's Altinity.cloud, which we run. It's been around since 2020. It's quite venerable. Runs on 4 different platforms. It is focused on, first of all, it runs any version of open source ClickHouse. So tell us the build you want to run. We can run it both our builds as well as the official builds, and it's very focused on BYOC, so bring your own cloud models. So these are all options that you have for running ClickHouse. I've given you 5, and as you're diving in, one of the things you want to do is just pick the right one for you and jump in. I've used all of them. They all work great. So That's the first thing that you want to know about. This is pretty basic, get you in the door kind of stuff. Um, the next thing is that we want to talk a little bit about what's going on in ClickHouse tables, and particularly the things about ClickHouse that are different, about ClickHouse tables that are different from other kinds of, from other um, uh, databases you may have worked with. Particularly, you want to think about partitioning, sorting, and compression, because these are the things that make ClickHouse column storage work. Let's talk about what those things are, because you may not be familiar with them. So ClickHouse tables are basically built to be fast. In fact, I could just say, I could make this uh, simpler. ClickHouse is built for speed. So when you look at the tables, you're going to see visible examples of this. So for example, we have this thing called the engine equals merge tree. That clause there, that's saying pick the merge tree engine. This is the standard engine. It has a bunch of variants, but it's a standard engine for high performance analytics on very large data sets. Um, we have compression that is just baked in. You don't see it here because when you make a merge tree table, it's going to default to LZ4 compression. You don't have to do anything about it, but you may decide to optimize it to get higher levels of compression than LZ4 offers. There's a partition clause which says, hey, break up the table into pieces by year. Um, and then there's an order by, which basically says within the table, what is the ordering of the rows that we'd like to have? These things, the compression, the partition by, and the order by are really important for tables. Why is that? Well, let's look a little bit at how ClickHouse works. So we're going to take a simple we're going to take a simple example of finding airlines with the most cancellations in a year. This is using a very popular data set called OnTime that you can just grab in. You can actually load it automatically if you're using Altinity.cloud. It's also very easy to access. But this is a query that actually would run in pretty much any database that you might care to use. So what it's doing is, well, you can read it yourself if you're a SQL person, but basically what it does is it comes up with the carriers that had the highest percentage uh, of canceled flights in a particular year. The thing to notice is how fast it is. So this thing actually scanned about 196 million rows. That's actually a small data set by ClickHouse standards. It did it on a relatively small host, only a few vCPUs, and it got back in less than about 2/3 of a second, and it was scanning at a rate of 300 million rows per second. This is quick. How do we do this? Well, the ClickHouse is optimized for reads, and there are two main kinds of relational databases or databases, SQL databases. There are row databases or row stores, and Postgres and MySQL are good examples of this. The default way that they store data is that if you have a row in a table, it's all stored in one place on disk. So when you read the one column, you actually have to touch all the values for the other columns for that row. So in ClickHouse, we flip that and we store the data in columns. This is, so for each column, there's a separate file typically. And when you read, you only read the exact, parts of disk that contain your column data and nothing else. Moreover, those columns are highly compressed. One of the advantages of putting the data in a column like this is it makes compression work much better. You can think of it as being arrays of data which have the same data type. These compress much better than rows with a bunch of heterogeneous data types. So we can illustrate the effect of how that speeds up queries with a really simple example. So taking that query, we can sort of walk through and figure out, okay, how much storage would that query have to touch in different situations? Let's see you had that data loaded on MySQL. Well, MySQL doesn't have very good row compression, so you would end up, and it's a row database, so you would end up reading 61 gigs of data off storage. It would be slow. In fact, when you run that query on MySQL, it just kind of goes away for a while. So that's sort of where we start. Now in ClickHouse, because it's a column store, right away, we're going to drop out most of the data. This particular table has 109 columns. We're actually going to read only about 1.5% of that data. So right there, we're down to less than a gig of data. We've knocked it down by a factor of over 60. Now, I mentioned the data is compressed. Well, if we go look at those rows exactly, we will find they're not 937 megs, they're actually 17 megs. So this is a tiny amount of data that can be read in a fraction of a second. Moreover, in a query, we're going to parallelize it. In this particular example, we parallelized it across 8 vCPUs. Each of those vCPUs only had to read 2 megabytes. This means that even something that requires us to touch every single row in the table can be done very, very cheaply, which opens up a lot of doors for analysis. So how do we make this work well? Well, this is where we get to the table definitions. So when you set up the table definitions in ClickHouse, a lot of the storage design is visible to you. So one of the first things that you will do is you're going to set the partitioning. And really the best practice for almost across a wide range of data sets is to partition by time. In this particular case, we're partitioned by year. The data set is not super large. It covers about 30 or 40 years of data. And so we just partition by year. We end up with about 500,000 rows per year, something like that. Um, so actually it's more than excuse me, it's more than that. But so we partition by year, and one of the things you want to look at when you're partitioning is try to choose partitions or partitioning schemes so that you end up with something like 1,000 parts or less. ClickHouse works best at that number. You can go much higher and it will also work, but that means that there are more files that we have to open up, and it will slow down, for example, it'll slow down restarts and stuff like that. So this is a standard best practice for partitioning. Typically do it by time. And why is time good? Well, one of the things that it does, in addition to other virtues of arranging the data in the order that people tend to look at it, so the hottest data is the most interesting. The other thing about partitioning data by time is that for many data sets, they receive about the same amount of data over time. So here's an example when we go in and look at the data. Um, there's about, for every year, there's something on the order of 6 million rows. If we were to partition by something else like carrier, you would get very, very lumpy distribution of the parts. You can see that the carriers, these are their names down below, or their abbreviations, they vary widely from a few 100,000 rows total to 30 million. So this results in parts that are very lumpy and hard to manage. Now, what we do, of course, within the parts is also important. That's where the ordering comes in. So in a system, many of you who are listening to this are building multi-tenant systems. And a question that comes up constantly for us is, hey, shouldn't we partition by the tenants? Because we really want to keep them separate. Well, the answer in ClickHouse is no. And I just showed you why, because tenants tend to be really lumpy. What we do, though, is we sort by them. So in this case, if you imagine this system as a multi-tenant system for airlines, we sort by carrier followed by flight date. That means if we're asking a question about Southwest Airlines, for example, the data will always be in the same location, sort of in a contiguous stretch of storage. This makes the queries vastly faster. So because we're minimizing the amount of storage that we have to look at for that Southwest query. So, and what you do is in a multi-tenant system, you'll order typically by the tenant, and then you can choose other fields, typically in order of decreasing our cardinality. That order by also builds an index called a sparse index that allows you to find these more quickly. But the key thing is the ordering. The index is important, but it's the ordering you want to think about, because that controls where your data is located. How about compression? Well, I didn't mention it and you didn't see it so far, and that's because when you're starting as a developer, you actually don't have to think about it very much. But ClickHouse has very powerful compression capabilities, and I'll just give you one illustration of how flexible it is. You can change the compression at any time you want. This is why we don't really need to think about it up front, because we can go in and alter the tables, even very large tables. We can alter them while they're online, change the compression. Here's an example of a very cool trick that ClickHouse enables. It's called a TTL recompress. And what it does is, in this table, after 6 months, it will recompress that LZ4 data and make it STD1. That's going to give us faster query and more important, perhaps for many people, less size on disk. And then after 12 months, we'll compress it to ZSTD1 10, which gets even better. It gets even better on disk compression. So this is an example of how you can play with compression at different times to get better cost efficiency. How do you figure out compression? Because I didn't mention that so far. Well, ClickHouse, and I'll just mention this once in this talk, ClickHouse has amazing system tables. They're the best I've ever seen. And this is the exact query that I was using when I was filling in some of the data in that example with the globes representing the sizes of the data. This is the query that I was running to figure out how big those three columns are. It's totally easy to do. There's also a system.parts table, which tells you all the data about parts, and there's a system.tables table, and that tells you all the data at tables level. It's very easy to, the compression is, and the uncompressed and the compressed size are just columns in this table, totally easy to find out. Okay, so this is how you pay attention to the care and feeding of column stores. There are many other things to think about in terms of optimizing schema, but these three things, the partition scheme, the ordering, and the and compression, are the three top things to think about. And one final reason for thinking about them early on is, once you've created picked a particular partition scheme, you cannot change it. ClickHouse, you'll have to, basically restructure the table, copy it somewhere else. And there are limitations to how you can change ordering. So it's good to think about them up front and get them more or less right. Let's go ahead and look at another issue, which is parts. We've talked about parts, and ClickHouse really likes big parts because, I'll show you why in just a second, but one of the things we want to do is think about helping ClickHouse get big parts as quickly as possible by inserting large chunks of data. So why is it that we like big parts? Well, the fact is that little parts and a lot of small inserts can crush your server. And so you can imagine, let's imagine something where you have like a bunch of devices. For example, they could be running FluentBit, or they could be using OTel collectors or something like that, and they're blasting just small chunks of data into ClickHouse from all over creation. What this will do is two things in ClickHouse, and let's illustrate it with a picture. We're going to, first of all, when you're doing a query, you're going to have to scan, when the data is newly arrived, you're going to have to scan a very large number of parts. Parts are expensive to scan. I mentioned that we want to have about 1,000 of them if we can get it. And so having a bunch of little ones will make queries very slow. I mean, literally double, triple, quadruple, quintuple your query time because of all the files you have to open and look at. The second thing, though, and this is the place where ClickHouse, where the small parts are particularly difficult, it causes ClickHouse to do a lot of work, because since ClickHouse automatically merges data in the background to coalesce the parts so that they are large enough that they're efficient to query. And so what will happen is, if you're sending a bunch of, say 10 meg parts, and many times a second, ClickHouse will end up doing a huge amount of work to basically to merge these so that it can get to something that's more efficient. We want to avoid this, because what this can do is it will actually bog down. It'll bog down your server, and you can get cases where, if there's a famous too many parts error that can arise, where you have inserts that are creating too many parts at once, and ClickHouse will just kick you out. So this is something you need to think about. So how do you do that? Well, In that particular case there where we're dealing with observability data, there's a couple of ways we could do it. One is if you're just loading the data with your own application, just load big chunks, put it in big files. ClickHouse doesn't have a problem with very, very large files. So this is an example where we're using the ClickHouse, what's called the HTTP interface. And what we're doing is basically blasting up a large CSV file and just using curl. And we're piping the data, the CSV data to curl, which is just pushing it to ClickHouse. This is a very, very simple way of loading large amounts of data because it's streaming through. It doesn't use a lot of memory. So if you have huge CSV files or Parquet or whatever, you can just blast them up exactly like this. And ClickHouse will happily put them in the table. And the bigger they are, the less the less work it has to do to merge them. So that's fix number one. Fix number two is to enable a great and very handy ClickHouse feature. It's called async inserts or asynchronous inserts. And the basic idea here is that if you have a bunch of clients doing doing small inserts, let's have all of those clients. Oh, 1 second. I'm gonna just briefly got one second here. I need to make a quick change on the webinar. Sorry about that. I have just promoted one of our support folks to come in and help answer questions. Okay, so back to async inserts. The idea here is that all of the clients that are talking to ClickHouse, they all have a connection. They send their data in, and basically what ClickHouse will do is it'll wait till we get a certain amount of data or enough time has elapsed, and then it will take all the data from all the clients and commit it and write it at once. It's kind of like a form of group commit. If you're used to relational databases, this is a feature that's existed for decades, but it works and it basically allows us to make bigger parts. So how do you enable it? Well, the settings are a little bit tricky. You have to play around with them, but basically there's 2 or 3 parameters that you want to set. Here are examples of how to do them. You can actually set them on the insert statement itself, but that's kind of painful. So what we typically do is put them in a profile. A profile is a group of settings that get automatically applied for a particular account. And so here's this user is called async. I've given it a profile that has the correct settings so that it will wait for like 10 seconds before things commit. So this is a great feature. It didn't used to be very stable in earlier releases, but now it's very it's quite stable and is really the sort of a standard tool for handling this problem. There's a final way to buffer things, and there are other ways to do this, but the third way that's commonly used is to use Kafka or something equivalent like Red Panda to buffer the data from the upstream producers and put them into ClickHouse. So this is a big reason, and many systems already use Kafka because they're collecting from many different sources, and they want to have things completely decoupled. So ClickHouse has quite good support for Kafka integration using something called the Kafka table engine. And the Kafka table engine wraps a Kafka topic and makes it look like a table. Every time you do a select off a Kafka table, you're actually reading from Kafka. And there's a standard way of setting this up where you have the Kafka table engine. You set up a materialized view. A materialized view fires automatically whenever blocks of data appear in its source table, and then it puts them somewhere else. And in this case, you have a merge tree table, which is the target. And so every time something arrives in Kafka, it'll buffer up, say to, for 10 seconds, you can set the you can set the timeouts and the amount of data it should read. And then as soon as it's exceeded that, it will go ahead and automatically select the data. The materialized view will then put it where it belongs. So this is a very simple way to have this integration. It scales very well. So these are 3 ways to give ClickHouse the big inserts that it wants. Let's go ahead and talk about joins. And for this, I would like to thank one of the one of the folks that signed up for the talk uh, who mentioned that, hey, I want to know more about joins in ClickHouse, and it's a great topic because we do hear, you know, sometimes, hey, ClickHouse can't do joins. Well, that's not actually true. ClickHouse does joins. It's a SQL database, just like any of them. And here's an example where taking that airline data set, we're going to go ahead and uh, select data, uh, destination data, for example. And in the on-time table, this is stored as an airport ID, which is, like a short and not very descriptive string. And you can see it right here. Those are the things that I think appear on your tickets when you're flying in the U.S. But what we'd like to do is we'd actually like to expand that out so that we actually have the full name of the airport in case we're going there in Uber and we want to look it up. So this join, those 4 lines of that you see for that join, that would work in practically any database. Uh, so it's no different, and it's pretty fast. Now let's look exactly at what ClickHouse can do, because this is where you start to see the differences. First of all, the join types. There's a huge number of joins. I've just listed the main ones between two tables there. Also, we also have the ability to do um, joins on what are called distributed tables, and we can choose to, for example, broadcast the data, or there's various ways we can uh, that we can handle distributed joins. I won't get into them here, but you have a wide range of tools. So, and in fact, including semi-joins, anti-joins, as-of joins, paste joins. These are all ClickHouse specific. Join types, as-of join, if you are somebody who works with market data, you've worked with KDB+, you know what an as-of join, it's where you have an approximate key. That's an example. Anti-join is bring the rows back if there is no match in the join table, stuff like that. So there's lots of stuff here to work with. There's also an increasing number of join algorithms. This is, as most of you know, joins are this is a deep topic of research. So we have at least 6 algorithms more on the way. But there is one thing that's important to know, which is that what ClickHouse does not do with all this, you have all these features, but they don't really work in BI style situations where you might have to make joins. For example, in e-commerce, if you're doing business intelligence, you might have to join a very large table of products with a large table of SKUs, with a large table of customer sentiment information. This is something that ClickHouse does not handle because first of all, it doesn't have a query optimizer a query optimizer that can really order the joins in such a way that it will do that efficiently. The second thing is it doesn't have very well developed ways of moving data around. So these are things that are still kind of hard to do in ClickHouse. However, there's a lot of work going on and joins are constantly improving. So we will see this problem solved over time. But when you hit this, you do have to put a little thought into it. So and I'll show you one way that you can address this that is different from most other databases. Let's dive in and just look at specifically how joins are processed. So if you don't say anything and you do nothing else, you'll get what's called a hash join. And the idea is that in that join that I just showed you a couple slides back, the left side is going to be your big table. And what we're going to do is we're going to go scan the data for that. And then the right side table or tables, we're going to put them in memory. So the first thing that ClickHouse will do is it will go and fetch the right side tables. It'll filter them, it'll filter that data, and it'll put it in memory. So it'll be just present in RAM, and then it will go ahead and scan the left side table. And as it's scanning, it will look at the hash table, fetch out matching data, and combine it. And in the end, you'll get a result. This is a very common join type. It's very fast. But one of the problems with it is that it requires memory. And it keeps putting often the same data in memory time after time after time. So one of the innovations that you get in ClickHouse is what's called a dictionary, which is basically, imagine if you could avoid constantly scanning those right side tables and just have them present in RAM all the time. That's what a dictionary does. So the idea here is that you load the dictionary, so in a separate query, and then you just have you basically have your in-RAM hash table, and now it can be shared by anybody who needs to join on that table. And the one of the big reasons that we do this is it's not just memory, but it's speed. It takes time to go and dereference this data and pull it into, decompress it, pull it into memory, uh, uh, make it available. And by putting this into a dictionary, we no longer have to do that. So this is great for reference tables, even fairly large ones, if you've got enough memory. Dictionaries are really easy to create in ClickHouse. So uh, here's an example. This is SQL that basically creates something that looks an awful lot like a table. And in fact, not only does it look like a table, but you can join on it once it's created. So you can just create it. You can just treat it as a table, and then you put it in the right side of your joins, and uh, and uh, and basically you get your data. Um, Another thing that we often do in ClickHouse is we just restructure joins to reduce data scanning. And with ClickHouse, as you probably are aware, everything is about speed. We make a lot of, because we're building systems, for example, observability systems where we're managing logs. We have people who have a system that's down. What they want to do is get into that log data, and they want to answer questions about that as quickly as possible. So the whole point of this system is to write SQL that will get results back in a second or less. That's sort of the target. Now we can join the data, but there's something kind of subtle that happens when we do a join like this, sort of just conventionally, and that is the join will get pushed down and actually be processed as we're scanning the data in the large table. That's not super efficient because it means we're doing lookups, but also we're dragging around a bunch of extra data. So for example, in this case, the airport names, they're getting dragged around in the intermediate results. So what we'll often do is we'll look at a query that's too small, and we'll say, hey, it's joining with a relatively small table. Let's rewrite that a little bit, turn it into a subquery, and the subquery will be the thing that processes the scan, and it minimizes the amount of data, and then we'll join on the results that come back, and that's much faster. And you can see an example where this dropped the query speed by a factor of 4 or 5. Um, in the fullness of time, this will probably be done automatically by the query analyzer, but right now you tend to do these rewrites yourself. There's one final thing. There are many, many things about joins, and I can't really go into them too deeply, but there's another way of thinking about joins, which is kind of where you begin to not just be a relational database person, but start to think like a distributed systems engineer. And that's to look at ways that if we have very, very large tables, particularly if we have data, people run systems where they have hundreds of ClickHouse nodes. And so and 50, 100 charts, something like that. The data that we want to join on is just not all in one place. Moreover, it's incredibly expensive to get it into a single place where it can be joined efficiently. So the question that we get then is how do we do how can we avoid doing joins in the first place? And here's an example that you get with device data where you might have devices that are reading temperatures, and you have restart times, and you have temperature readings from the same device. And what we want to do is we want to get aggregates of the data that joins restart times with temperature readings, so we see them in the same row. And so this is a case where many databases would force us to do what's called would force us to either join tables. We'd put them in two separate tables and then join them, or we could put them in a single table and do what's called a self join. And but for many databases, even in this case, they're still going to have to scan the table twice to get the different entities out. In ClickHouse, we do this a little bit differently. So one of the things sort of a hint about how you solve this problem is to think about aggregation. And aggregation is very powerful. Unlike joins, which often have to proceed in steps where you join two tables, join another table, aggregation works in a single pass. So the question is there a way that we can make joins be like aggregation? And in fact, that's exactly what we do in some cases, like this one in ClickHouse. We have something called conditional aggregation. And so what this is with this temperature data, this is a table that has about 1 trillion rows of test data in it. And what we've done is we have the reading data data and the restart data are just in the same table with different columns. And then what we can do is we can use what's called a conditional aggregation. So for example, this min if says, hey, take the min of this value if it's a reading. And so it gets aggregated. This is different from processing something as a null. It's not null processing. What this is doing is saying only do this aggregation if you're looking at a row which is of type reading. And what this amounts to then is, or what this results in, is we can scan the data in a single pass through and get the results we want without having to do a join. For large tables, this is really powerful. This is a trick that I learned from one of our users who does it on trading data, but it can be used in a wide set of cases where you have multiple types of entities and you just put them in a single table and then lean on aggregation. Okay, so we're getting close to the end, and the last uh, lesson or the thing about ClickHouse that you should know and that I really like is that ClickHouse prioritizes speed and scalability over everything else. Want fast or you want transactions, you're going to get fast. That's why ClickHouse has not spent a huge amount of time on transactions. You want BI joins or you want fast. Well, ClickHouse is going to prioritize fast. So you can come in and you can see these as, oh, these are deficiencies in ClickHouse. But there's another way to look at it, which is that this is a different way of looking at large systems. And why is that? Well, when you're designing really large systems, for example, very, very large data sets, it's simplest to think about them and most cost efficient if as much as possible you can work with data that never changes. Why is that? Well, changing things is expensive. Like going and looking up a row to delete it is an expensive operation if it's spread across 50 million, 50 servers. So, or if it could be anywhere in 50 servers, that's just an operation that we do not want to do because it's going to slow us down. Another thing is that if data is arriving very quickly and we want to be able to accept it as quickly as possible, we need to accept the fact that receiving that data and being completely consistent across receiving that data quickly and being consistent across the entire system, like having everybody, for example, see the same version of that data at the same time. That's very, very expensive to do. And and that's the reason why large systems tend to use some form of eventual consistency where they, as a trade-off to improve response, for example, to improve insert rates, they tolerate the fact that at any given time, nodes will see somewhat different views of data. So these are two types of trade-offs that are really important in these large systems. And ClickHouse kind of revels in that. And I'll give you an example of where we use this to solve the problem of updating rows. This is very common if you, for example, if you have a data set that's being constantly fed new data. Let's say that from time to time the data is needs to be changed because you misread something or like the value of a security has changed and you want to update it. That kind of update is very expensive if you have a very large data set. But there's other ways that solve this using the notion of immutable data, so never changing things, and then eventual consistency. And it's called a replacing merge tree. This is a table type. And what it does is it automatically deduplicates the rows in the order by. So this is a different table organization from plain old merge tree, but the basic idea here is that any row that arrives that has that matches the language ID, studio ID, and film ID. This is taken from a MySQL example. It's going to assume that those are all the same those are all the same rows. Moreover, you can have another column which is called the version, and that version is going to be used to decide which of those rows should be the winner. This is a classic way of handling eventual consistency. Is you have a series of possible values, and you're going to have a way of picking the one that you should actually show. So so that and this is an example that's actually taken from replicating data from MySQL, but you can use this in many different ways. How does it work under the covers? Well, um, as these row values arrive, what's going to happen is you'll put the initial value in, and let's say you give it version 0. You could use a timestamp, anything. There's a bunch of different ways you can do this. So the first value arrives, it just gets inserted. Fine. Now you get a new data which needs to update it. Here's the next row. So what'll happen is ClickHouse will use that value to override the first one. And then finally, you get a final value. Maybe it's deleting this. In this particular example, it actually was, but we're going to deduplicate and only hold the last row value. So, but there's kind of an interesting effect of this since we're just inserting the values in. If we just naively select them back, we might actually find that we see multiple rows, because what happened was they were inserted, and as you've seen before, they go into different parts, and those parts have not merged yet. So we'll see two values. Well, that's bad. What we need to do is now do a little bit of extra work so that we can actually merge these rows. And what happens is the rows are replaced when the merges occur. So when the blocks get merged, these values will basically just intersect in the sorted, as the data is sorted, and ClickHouse will pick the last one using that version field. It has a default way of picking it as well, but I don't totally trust it. But here you have right here that once it's merged, the data will become consistent. There's a problem though. ClickHouse is designed for really big systems, and in really big systems, we don't have a guarantee that the data will ever fully merge, because parts at some point reach an optimum size, and at that point, ClickHouse no longer merges them in the background. So what we need to do is just a little bit of extra work to handle that case, and that's where there's this important keyword called final. And what this does is this final keyword then says that, hey, at read time, do an extra scan and make sure that within, for example, within a part, and there's a little bit of design around this, but within a part, you don't have multiple copies of the data. Make sure that you've fully merged them before you run aggregations and present them to the user. So that's how that's basically taking this notion of immutable data, eventual consistency, and giving us a way to update rows, to do deduplication. One of the questions that came up in this is like, how do I do backfills, which may actually alter data? This is a very common operation. I have screwed something up. I'm going to do a backfill for 2 months. How do I actually override the data that I have out there? This is one of the ways that you can do it in ClickHouse without having to go in and do updates on all these rows. ClickHouse uses this notion of basically being able to have things which deduplicate or merge based on their order by. So the replacing merge tree, I showed you how this worked, but we also have for aggregations, we have summing merge tree and aggregating merge tree, in which case the order by becomes effectively your group by key. Collapsing merge tree and version collapsing merge tree are sort of variations on RMT that are older and a little bit less used. There's a really interesting table type called coalescing merge tree. And this is kind of like the replacing merge tree, but it solves a slightly different problem. Suppose you had metric data. This is a problem that comes up in metrics a lot. Suppose you had different metrics for the same device that happen to show up at at different times. You'd like to get them all put together in one row and then use that for queries. That's in fact exactly what the coalescing merge tree does. It will deduplicate, but when it deduplicates, it in fact unions the data. And so for example, you could have one row inserted that just had a value for one, as this thing shows. When they actually merge, you're going to get 1 and 2 in one row. And again, when you put the final on it, it will ensure that this happens. So this is a recently added table type. I don't know who implemented it. It was one we were thinking of doing, but then somebody else did it. But it's a really interesting example of how to solve this problem. Okay, so I see one question. If you have other questions, please do go ahead and queue them up. We'd be happy to answer them. But very quickly, so things that you should know about ClickHouse as you're coming to ClickHouse, particularly from other databases. First thing, there's just a bunch of different ways to run ClickHouse. And this is sort of, there's a, beyond your own convenience as a developer, another way to think about this is depending on what cost efficiencies you're looking for and level of convenience, how much you want to manage, how much you don't want to manage, you can put ClickHouse anywhere you need to. You can run it yourself. You can do a huge amount of stuff just on your laptop, particularly if you're running on Linux or WSL2 like this machine. Um, you can do a huge amount of stuff just straight off your laptop, but then you have a bunch of different choices for production deployments. So look at them. They have trade-offs, but there's basically anywhere you want to run, there is an option for you. The next thing is, as we saw, column data is, or columnar data is what makes analytic systems fast. That's one of the fundamental innovations in these systems, along with being able to query things in parallel and to do fast aggregates. But you need to pay close attention to the partition by, the order by, and then as your systems grow, you want to look at compression. And I should add that with compression, one of the problems with performance in ClickHouse is, and compression illustrates this, is if you're dealing with a couple 100 million rows of test data, you won't see a lot of performance problems because ClickHouse is just so fast and is able to parallelize that you may not see them. But when you get 1 trillion rows, they will become very obvious. So think about those, look at compression levels, try and fix them early. You want to make inserts as big as possible. This is just something that's true across analytic systems in general, but there's some very specific problems with ClickHouse that you can avoid if you have big inserts. Async inserts are probably your #1 way to solve this problem. Joins. ClickHouse, they are definitely different. There is a huge amount of roadmap work on this. So if you go look at for example, the 2025 ClickHouse roadmap in the main ClickHouse repo, you'll see a lot of work on joins. So this is continuing to improve, but you need to understand how it works inside and think about some of these alternatives which allow you to get joins basically to return in constant time. That's that trick with aggregation I showed you that gives you that performance. And then finally, immutable data and eventual consistency. These are tools that we use or concepts that we use to build very large systems. And ClickHouse has features that use them, and it's helpful if you can use those features and you can also think about them as ways to build your own systems. So with that, we're done. I'd like to invite you to we are sponsors of an open source analytics festival that's going to be at the IBM Silicon Valley Lab next Thursday, July 31st. So there's a QR code. You can go ahead and look at that, or you can just Google Open Source Analytics Festival, and that will find it. So hope to see you there if you're in the Bay Area. Love to talk about these topics. And beyond that, thank you very much. I hope this talk was helpful. And we do have a question I see. Maciej, you want to take this one? What's the best way to deal with pre-1900 dates and date times? Any suggestions on that?
I do not see that question because I rejoined later. Can you repeat it, please?
Yes, is what's the best way to deal with pre-1900 dates and date times?
Uh, hmm, I'm not sure if I catch it.
Yeah, so you have like if you have a date that's so for example, if you're using a Unix date time, I believe they go back to 1970. In fact, we could say pre-1970. How would you deal with a date that's prior to that? In
Uh,
fact, for the person who
yes,
wrote this, it'd be interesting to know what your use case is if you want to type that in.
yes, there's a datetime 64 type, and it uses 64 bits for storing it, and you can convert basically it forth and back to that type, and it should
Yeah,
be wiper. So
yeah,
if you have like dates like that, you should use that type.
yeah. Oh, here's a great one. Oh, thank you, Anthony. So Anthony has just followed up. So Daytime 64 now supports back to 1900. So what do you do? So I'm just like picturing, oh, so I could see this could be like weather data or something. This is an interesting problem. We normally get people who they want to know like what happened in the last 7 days. So or year or something like that. That is that's an interesting question. So I mean, obviously you could do a hack, which is that
Yes.
you could come up with some
Uh,
scheme using
Second
intervals
column
and
with minus, I don't know, years.
yeah,
And
exactly. Yeah,
values.
just yeah, some sort of negative values. This is a really good question. It would be very helpful to understand what your uh,
Use
what your use case is because there may be other ways of thinking about it. If you want to expand on it, feel free to join our Slack and post this. Historical weather data. Okay, that's what I thought it was, or that was one of the possibilities. Yeah, that's an interesting case. Um, yeah, Michelle, I think I would construct some. Unfortunately, ClickHouse doesn't really have user-defined types.
second column
So,
and a function, custom media function, convert it back. But basically, it
yeah, yeah,
won't be
that's a great idea.
binary because it's not like possible.
Yeah,
Yeah.
think about. Oh, go ahead, please. Sorry, didn't mean to interrupt.
Yeah. So you have function and basically convert it because later it needs to
Yeah,
be read somehow.
yeah,
So this is up to you how you want to read it. If you can like store them in strings, but then you won't have the ability to use all that datetime functions. So uh, it will be best to have that datetime 64 plus some other column that will tell you how many years, months it needs to be decreased and so on. So right now it's I don't think it's possible to do with one column or use
yeah,
your like custom uint and convert it custom because
yeah,
again, I'm not sure about the steps. It should be seconds, minutes, hours. So yeah,
yeah. I it feels like you might want to do something with UDFs to user-defined functions to try and encapsulate those time shifts. Um, UDFs and ClickHouse are pretty handy. Um, the and particularly you can write them in Python, which is not necessarily super fast. But for example, if you write a little C++ program, that actually is quite performant and pretty easy to integrate with ClickHouse. So this is something where you would write a little bit of C++ code to do some of the conversions for you, make them run really fast.
if that conversion can be written in SQL, then it will be the best because there will
That's
be no
right,
like
right.
external dependencies. So
Yep. Yeah. So if you have something you want to try out, feel free to join our Slack, post that question, and we'll have a look at it and see if we can come up with other schemes to handle it. Um, with that, any other? Oh, here we go. Yeah, so it's only a relatively small subset of the data we need to handle, so I like to avoid customization if possible, but thanks for the suggestion anyway. Yeah, it's a tricky problem. I'll tell you what, on dates, I think the biggest thing we put in the daytime 64 type we originally implemented. And the big reason that we put it in was for trading, particularly high frequency trading. They there's a or any kind of automated trading, you want to be able to order timestamps, and the normal millisecond, sort of being milliseconds is just far too large for a lot of those applications. So Daytime 64 gets you down is focused more on getting you down to nanosecond uh, uh, level of discrimination of time values. Let's see. I don't see any other questions at this point, so I hope you enjoyed it. If you do have further questions, you can contact me on LinkedIn. By the way, I'd like to thank the folks on LinkedIn who responded. I hope the material covered some of the questions you had. Feel free to contact me directly, join our Slack, or just come to altinity.com if you want to contact us for other things related to ClickHouse. So with that, thank you very much. Josh, thank you for helping with organization. Machet, thank you for joining to answer questions, and have a great day and have fun with ClickHouse. Talk to you soon.